The topic is a simple harmonic pendulum. We'll start with a simple demonstration of a simple pendulum. Here I have a string. At the tip of the string I have a little mass attached. I'll show you two different cases. One is a long string, another one is a short string case. Let's compare what difference is. Now we'll make the string shorter. We'll make it longer again so we can compare. As we saw in demonstration, when string is long, one cycle of the motion takes a longer time. When string is short, the cycle takes a shorter time. Then how do we calculate that time? To do that, let's draw a diagram like this. We have a mass attached to the string. As long as you have a mass, there is a gravity acting on it. So mg straight down to the ground. I call this length of a string, which is equal to radius of a circular motion. I call that L. The force by gravity, only a portion of that is contributing to this motion, which is tangential component. Say call this the angle between string and vertical line, say call it theta. Okay? Then that theta is equal to this theta because these two lines are parallel. Now tangential component will make arrow. Imagine there is a imaginary line here. Then we have a right triangle. So this right angle. So using trigonometry, we can find this tangential component to be mg sine theta. Now this force acting on the mass is always against the motion, which is downward, okay, against the motion. So we have negative sign, negative mg sine theta. Newton says by second law is force mass times acceleration, so equals to ma. But acceleration is a second derivative of travel distance. And here travel distance is along this arc line. I call this arc line S. Okay? Travel distance along the arc length. So m second derivative arc length equal to minus mg sine theta. Now both of them has m. So we can cancel m out. What's remaining is negative g sine theta equals to second derivative over arc length, which is travel distance. This arc length s, we can write using circumference expression. Circumference is, for total circle, is 2 pi times radius. Radius here I call it L, so 2 pi L is circumference. The arc length of this motion is simply just a fraction of that. Okay. Angle theta out of 2 pi, that's a fraction, times 2 pi L gives you L theta. You plug that into S, then negative g sine theta equals to L is constant. Okay. L is constant, so second derivative of angle theta. So we have a second derivative equation. Now, for the calculation purpose, sine theta we can expand using Taylor expansion. Let's call sine theta be a function of theta. Taylor expansion is given in this form, okay? Summation of many terms. First term is just evaluate the function at certain value we are interested in. Here, what we are interested in is a small angle. Okay? This pendulum motion is a small angle. It didn't go up high like this. Okay, a small angle. So, which means we are interested in near zero. Okay, near zero. So here in this formula, Taylor expression formula, A to be 0. Okay? So using Taylor expansion, if we write, first term is simply function evaluated at 0. Okay? Second term, we take first derivative and evaluate at 0 and divide by 1 factorial and multiplied by variable. Here is theta is variable, theta minus 0. Third term is involving second derivative, evaluate at 0, division by 2 factorial, and theta minus 0, power 2. It goes on, power increase and denominator factorial number increase. The function we have is sine theta. Sine theta's first derivative is cosine theta. Cosine theta evaluated at 0 is 1. Sine itself evaluated at 0 is of course 0. That's this term. Now, second derivative of sine is a negative sign. Evaluate at 0, sine 0 is 0. Higher order terms, let's think about it. In the parentheses, theta minus 0, this angle we're looking at small angle. So this is small number. The small number take higher power, then gets much smaller. More of that denominator, number is increasing in factorial. Big number factorial is dramatically increase. So we have a very small number on numerator, very large number on denominator, which means that term goes to almost 0, negligibly small. So we can ignore those higher terms to approximate. So what's surviving is only this term. This is 1 factorial is also 1, so simply the second term is theta, which means sine theta is approximately angle itself theta. Angle itself theta is the same as sine value of the angle. So can we write the equation negative g theta, not sine theta now, we replace sine theta with theta, equals L times the second derivative of angle theta. So we have a second order differential equation. Theta double prime plus g of L theta equals 0. To solve this differential equation, you can use initial equation, which is r squared plus g of L equals 0. From this we can write r to be plus minus complex number and square root g over L. Now here square root g over L, let's call that to be omega. Okay? We call square root g over L be omega. Once we have a root expression of our initial equation, then you can write the answer of the differential equation. The theta that we want is some constant times cosine omega t plus another constant sine omega t. Using true identity, which is cosine alpha plus beta, is cosine alpha times cosine beta minus sine alpha times sine beta. Using that, we can rewrite that in this form, cosine omega t plus epsilon. Epsilon is a constant. If we expand this out using true identity, you get the first equation form. Because the cosine epsilon is constant, will be embedded in C1. Sine epsilon is also constant, will be embedded in C2. Now here in the parentheses of cosine, omega t plus epsilon, there is nothing but theta, which is angle. That's angle. Okay? Epsilon is constant. Omega t is changing. Time t times certain value omega gives you angle. Of course, that omega will be angular speed, which is 2 pi times frequency, 2 pi f. Frequency is the reciprocal of a period, so 2 pi of t. But omega, we called it to be square root of g over L. So we can write period equation t equal 2 pi squared L over g. Now we have expression for period. Let's think about it with the demonstration we had at the beginning. When we had a long length of a string, it was taking a longer time to make one cycle. Let's look at it. T is large, numerator is large. L is large. Of course, T will be large. If L is small, which is when we had a short length, of course, period will be short. That exactly matches as we had a demonstration. Now let's think about G. Of course, on the ground level, G is known to be fixed as 9.8. But the G value, if you say you climbed up to the top of a mountain, like high altitude, like Everest mountain, then this G value will be different. This G value will decrease. As a G denominator decrease, then T will be increasing, which means you bring same pendulum clock to the top of a mountain, then the clock will be going slow. Let's think about another case. Say you brought same clock, pendulum clock to the moon. The moon has much less mass than that of the Earth. So the G value will be smaller. G is small, then T will be large, which means that pendulum clock, if you take that to the moon, your clock will be going slower. Okay, it's been a simple harmonic pendulum. Thank you.